This is a lesson on composition with quadratic functions in a precalculus course. In a previous lesson, I had introduced composition of functions. We had went over a couple of different strategies for composition of functions. The first one is carry out usual algebraic operations involving addition, subtraction, multiplication, and division. Okay, so I introduced that with linear functions, but now we're looking at it in regard to mathematical operations with quadratic functions. So one I picked out here that students have trouble with, and what I'll say here is, for me, a lot of the operations, either if you're doing just mathematical operations or the next strategy with composite functions, is algebra, to polish up on your algebra and have your eyes start recognizing things that you need to see. So for instance, in this situation, I'm going to take f and divide by g. So that's not hard to do. I'm going to take this guy and write it out and divide it by this guy and write it out. And in theory, I'm done. And you may say, I did it. I divided them. But what your eyes are being trained to do is to get into simplest form. And maybe the problem may say that. Simplest form. You need to always get your expressions into simplest form. This is not simplest form. Like I mentioned before when I reviewed factoring, you're making your eyes watch out for situations where you might be able to simplify something, right? What I'm going to notice is that I have this linear term down here, right? And when I look up top, I'm like, what'd be cool is if this guy up top factored so that this is one of the factors. So what I'm going to guess is the top factors into this times another term and then this down on the bottom. So you may recognize this from before when you initially studied, simplifying with factoring. You may have covered this where you'll end up dividing on top and bottom, and that bottom here is a hint, like you can factor it. Like, to me, I take it as a hint that there's that this will be one of the factors. There's a -3 here, so that means I need a x plus 1 up top, and indeed both of those cancel, and so this is going to be the simplest form of that, and why an answer like this wouldn't be accepted, because it's not simplest form. Another problem I picked out to do here as an example is subtraction and a domain, right? So we're going to remember to write the domain down. Don't let me forget to write the domain down. Given f of x is this and g of x is this, we're going to do a subtraction. You're like, okay, I can subtract. That's pretty easy. 5x over x minus 3 minus 4 x plus 2. So what we need to do is get a common denominator. We do not have a common denominator. So what I need to do here is multiply the original two terms by a factor of 1 in order to get a common denominator. So a common denominator that we're going to want is x minus 3 over x plus 2. That's going to be our common denominators. We're going to multiply those two denominators together. There's still a minus here, but I wanted to leave space in order to say I need to multiply the first term by x plus 2 over x plus 2, right? A factor of 1. That's a factor of 1 overall in order to get this common denominator, and I need to multiply the second by x minus 3 over x minus 3 in order to get that common denominator for both of those terms. So this will have that same denominator as that final term that we're looking for. So I'm going to have to multiply here. I get a 5x squared plus 10x over this stuff minus 4 times x minus 3, so that's minus 4x plus 12. Hopefully you followed that distribution of that negative sign in there. Don't forget that negative sign. So that's what I'm talking about as you're going through and polishing your algebra, is making sure you're multiplying and foiling and everything and keeping track of your signs. A lot of times students will lose signs and then think they don't understand math at all, but it's just a sign. 5x squared. Does this guy need an x? Yeah, this is 10x. 5x times 2, that's a 10x. So I get plus, see, I just did it. I had an issue on it. See, I had a math error in there. So watch out as you're doing everything accurately. And then we get x minus 3 over x plus 2. I would say if you wanted to, you could go through and see if that the top factors. I would say if the top factors, there'd be a factor of x plus 2 in it, because the other one is x minus 3, and there's no negative signs up here, so I can't get an x minus 3 factor. So I guess that means that this would have to be 6, and this would have to be 5x with a plus, and I don't think that's accurate. Right? 6x, this would have to be a 16x, not a 6x. So it doesn't factor. It's not factorable. Okay. But what I did do for you all that I want to look at is I looked at the graph of this. Because remember I said don't let me forget to do the domain. When I do the domain, and this is why they make you do domain, just reminding you, students have told me they still struggle with domain at this point in precalculus. What I'm going to notice is in my original functions, you remember in our original functions up here, we have denominators. And the composite, right, when I do a composition of functions, whatever were boundary conditions on the first functions, those carry over to be boundary conditions on the composite function. So I know that x cannot equal 3, and I know x cannot equal negative 2. So when I look at this graph, when I put this function in here, and I already know this by this denominator as well, is I can't put those values, those are not within the domain, because that would result with a 0 in the denominator, and then like the world explodes or whatever happens when there's a 0 in the denominator. So if I go back over here to this graph that I was going to show you, you're going to see on here asymptotes. All right, so I had mentioned this term before, and I'm going to still mention them because I know them. I'm not going to pretend I don't know them, even if you don't know them. And we're going to see that there's a vertical asymptote here, and there's a vertical asymptote here, and we're not going to be surprised to see that those values, and note that every mark in here is 2, that there's a negative 2 and a positive 3. Is that accurate? Did I say that accurately? Is there a positive 3? Yeah, I think maybe it doesn't go up enough, but I know it goes there. There's a positive 3 in there. You can see right here it goes, it's getting closer to that 3 value. It never gets to 3. I originally drew it on 4, but it needs to be on 3, right? So when you're giving that domain, right, the general form here, when you get this algebraic expression, it should tell you, but if you're not 100% certain, look at it on a graph. So when I look at this, I'm going to have a union of 3 different regions. This is a union of 3 different regions. I'm going to have some negative infinity to positive 2, and it can't equal negative infinity, and it can't equal, negative 2. This is a negative 2. I'm going to union it for that region between negative 2 and positive 3. You can see it's negative down in there. That's that little portion here. So I'm going to say it can't equal negative 2, and it can't equal 3, but there's definitely a domain in there where I have real numbers. And then also this final region, when it's on the right side of the graph, is from 3, a positive 3, all the way up to infinity. And so that would be the domain for this function, this composition of functions result. The next thing I wanted to move on to was composite functions, and I've been a little bit sloppy because I'm saying composition of functions and composite functions. Composite functions are a strict definition where I'm putting a function into another function, where I take g of x and I plug it into f of x, and there's the specific notation with that little o, that dot sign in there. All right, so and again, we're going to remember that the domain of the composite function is limited by the domains of the original inside function. Most of the time at this point, students are doing okay with this, especially with quadratics. There may be some algebra simplification involved, but you're doing okay on it. What I see students struggle with is applications where you're taking functions and you're putting them into other functions. And so I see this sometimes, the area of an oil spread. I picked this out as an example. The spread of oil leaking in the ocean. I would say a spread of oil. I don't know. There's bunches of spreads of oil in the ocean, unfortunately. And the spread depends on how fast the oil maybe is being supplied or the viscosity of the oil. There's different factors that go into it, right? So in the ocean is a form of a circle. How convenient. We know the area of a circle. Pretend that's my perfect circle of oil out in the ocean and it has some radius r. And what it tells us is the radius of the oil spread after t hours, all right, there should be a t there, is r of t. So this radius is getting larger. It starts small and over time, as a function of time, it gets larger, right? So that radius increases as a function of time. And that's the equation for it. Find the area of the oil spread in terms of time t. So when I think about the area of the oil spread, here's the area of the oil spread. Convenient, I know the area of a circle, right? That's why I said it was convenient. I know the area of a circle as a function of the radius is pi r squared. I know that. And what they tell me is that the radius is a function of time, 175 root t for me. This could be any dependence on t, but in this situation it happens to be a radical. All right, and I picked this problem out because here's the parabolic term, right? It's going to increase as r squared. So what happens is if I take these two, if I take r of t and put it into a of r, I'm going to get an expression for an area with respect to time as a function of time. So what I'm going to do is take my area equation, pi times r squared, and wherever I see r, I'm going to put 175, the square root of t. So this becomes a nice linear expression, 175 squared times pi. So I always put the number first, and then I'll put pi first, and then I'll next, I guess, and then I'll put the root t squared, which just becomes a t. And that's how I will order those when I go to properly express them. 175 squared, I multiplied that out at some point. I forgot exactly what it is. Oh, I see it here. 30625 pi times t. So the area as a function of time increases linearly. It'll be a linear expansion for that area, even though it's a two-dimensional object. So that's kind of interesting. So that's how you would do that problem. Another problem I see students struggle with composite functions in here is this problem. And admittedly, I would too. Not necessarily, and I think this is the same for both of us, not on the find the composite function. So what they have here is a number of bacteria as a function of temperature, and the temperature is a function of time, okay, where T is in time hours, all right? The temperature is in between 3 and 33 degrees. So big T is temperature and little t is time. To highlight that math and most of the sciences are case dependent. A big T is not the same as a little t. Little t is typically time. Big T is typically temperature. All right. So A, find the composite function. All right, this sounds fun. I'm going to find n of t. The number of bacteria as a function of time is going to be the number of bacteria as a function of temperature as a function of time. So wherever I see T of t in here, wherever I see a big T in this equation, I'm going to put this whole dang expression. So I'll have 27 times 6t plus 1.3 squared. Don't forget the squared in here. That t is squared. I'm going to subtract off 71 times 6t plus 1.3. And then I'm going to keep this plus 11 on the end. All right. And miraculously, even for me, if you wrote this out, I would not make you simplify it anymore. And I don't believe the computer makes you either. You can just enter it into a text box like that if you were given it as a problem. All right. The next part, though, is where I see students struggle. Find the time when the bacteria count reaches 9975. That's what I was given, 9975. So what I do is identify this number, right? Words mean things, and when I'm given information in a word problem, it translates into something that is relevant for my problem, right? So to solve algebraically, I'm going to recognize that this is n. This is the number of bacteria, the bacteria count, the number of bacteria, n of some time t. I don't know what time t. They say find that time. So I know n, but I don't know t. So what I can do is say 9975 equals 27 times all that stuff. All right, all this goes down in there. That is equal to that. And I think that looks intimidating because what it looks like you need to solve is solve this equation. And what I see students do, and I'm just writing this out so that you can see how intimidating this looks. What I see students do is say, oh, I want to flex my math muscles and I'm going to multiply and FOIL that out, and they'll write out 10 pages of algebra in order to be able to solve that equation. And I'm not saying that you're going to get the wrong answer. I think you're going to get the right answer, but what I'm saying is you're doing the work hard rather than work smart method of solving this problem. Okay, so if I were to redirect you into a wiser way of solving this problem, this equation is true. That's absolutely the equation that I need to solve. Okay, but what I'm going to notice is that in order to use a quadratic formula, let's say I want to use the quadratic formula on this, I'm going to get an a factor, a b factor, and a c factor. I'm going to have to move that 9975 over. So I'm going to get 0 equals 27, 6t plus 1.3 squared. Those are still true. That doesn't change anything about these terms, and I'm not going to multiply them out. I'm not going to do that. I'm going to show you what we're going to do instead, right? We're going to make this smart, not hard, all right? So I'm going to take 11 and subtract 9,975, and then that will give me a 9,964. You can plug it into your calculator. I'm pretty sure I'm right. What I'm going to notice here is that this is still T. This is still big T, right? That's still a temperature. So I could write it like this: 27t squared minus 71t minus 9,964. And pals, that's what I would do. I would solve for t. And you're going to get what? T is going to be 71. If you do a quadratic formula, you're going to plug it in and do this stuff, right? Minus 4ac 27 times negative 9964, right? And then divide by 2 times a, 2 times 27, and you're going to have a plus or minus, so you get two answers, right? Only one of them is real. And you can do that. That's how I would solve it. Once I get t, what I'm going to notice is t is still equal to that. So I would just take those two values I get and set it equal to that and solve for little t time. But even easier than that, my friends, and why I am here, why I exist as your instructor, to show you that I would just bring the graph up. If you aren't clever on that already till this point, I would not solve this algebraically unless I was forced into a corner by a math teacher and they made me do it. Otherwise, I'm not going to solve that algebraically. I'm going to get a graph out. What you're going to notice is that I'm pretty sure I put in this blue line that I had here. When I put it in there, I see that it gives me an answer, right? When I plug in this, I plugged in the original function. That's what I did. I plugged in this original function. I plugged that in, and I put an x here instead of t, and an x here instead of t. I know you can't see it behind the graph here, but that's what I did, is I put an x there instead of t, and I plugged that original function into Desmos. That's exactly what I did. I didn't make it any harder than that. Once I have this function, I'm going to plug it into Desmos, and it drew me this parabola. And then what I did is I drew the line y equals 9975. And so when y equals 9975, it tells me the answer. It just told me the answer. I just will put that into the computer, is read the answer off that graph. I didn't even solve the quadratic equation. I didn't do 10 pages of algebra. I just used the graph. So I think that's where students get intimidated and confused and bogged down with this problem, is they don't see the elegant, work smart, not hard way to get the answer to this problem. So hopefully, again, another primate watching me solve problems, you're going to catch on to that strategy, like, oh yeah, that's what the graph exists for. I'm going to find important points on the graph that I know how to find the algebra. I know how to do that algebra. I'm not going to do it if I don't have to. And I'm going to use that graph if I have to do the algebra. It's going to verify my answer down there. So those are some tips on doing some of these composite function problems.